Hi everyone, this is chapter 6 queuing models. This chapter will be covered in 2 weeks, so this is section 1 for this week, and it will be presented in 3 parts as pre-recorded videos. So this is part 1. So on our course map, we just completed chapter 3, general principles of discrete event simulation models. And so far, we know all the concepts about the simulation. And we know that how we can model a system in terms of a discrete event simulation models. So these two chapters, chapters 5 and 6, we have these two chapters inside here in this course map. So this means these two chapters are not directly related to a simulation, but they are somehow supportive and background knowledge that we need to know. So the statistical model here will be a review on the course of statistics that you had before. So this chapter will be reviewed in the tutorial session by Ansel. And now I'm gonna uh, start chapter 6, which is about queuing models. Okay. What's a queuing model? Here, assume that we have a system like this. In our system, actually, we serve customers. We do some processes to serve customers. So customers arrive the system from the outside of the system. So here we assume that we have a calling population, and it includes all potential customers. So these customers arrive the system. They will join a queue and will wait for a while there, and then eventually they will receive the service by a server, and then after that they will leave the system and will get back again to the calling population for a future service request. Okay, so this is called a service system, and it's and a queuing model is a model of this kind of system. Okay, so here we have the term of customer here, and generally customer is any type of entity. It's not like a person. It's not, yeah, it could be any type of entity that needs a service or a process by the system. Okay, so the examples are service facilities, production systems, repair and maintenance facilities, and so on. Okay, so as you remember, I can say almost all the models that we had so far in chapters 2 and 3, except the Monte Carlo simulations for the inventory systems. Yeah, the rest of the examples all are about a queuing model. If you remember, over there we had entities, let's say customers coming from the outside of the system, and then they will join actually a queue, a line, and then after a while they'll receive the service and then leave the system, right? So yeah, I mean, this is called in general a service system, and we have queuing systems or queuing models to formulate or model these kind of systems. Okay, so we model the queuing systems, I mean the service systems, as a queuing model, and then we analyze a queuing model to obtain some performance measures, right? In order to use those measures in analysis or in design of such systems, right? So uh, so for example, the measures that we need to obtain in order to analyze or design a service system uh, could be these measures: server utilization, length of waiting lines, and delays of customers. Okay, so as I said, a queuing model can be analyzed mathematically or through simulation. Okay, so the queuing theory is a theory here. The queuing theory analyzes the queuing models in mathematical way. So the mathematical study of queuing models is called queuing theory. Okay, and we also saw in chapters 2 and 3 that we can simulate those systems as well, right? So we can analyze the queuing systems by simulation as well. Okay, so we have two actually ways here. One is using queuing theory and analyze a queuing model, a queuing system in mathematical way without simulation. And the other way is using simulation. Okay, but as you know, actually, we can usually use the mathematical models or queuing theory for simple queuing systems. Okay, so if the system, I mean, the server system is simple enough and can be uh, analyzed by any of the available queuing models. So we will do that. We don't need to use simulation here. But if our system is complex enough and cannot be analyzed by the mathematical models or queuing theory, in that case, we need to go for simulation. Okay. So for very simple systems, we can use, as I said, the queuing theory, the mathematical model. And for complex systems, we usually use simulation, right? But for complex systems, still we can use the mathematical models. If we consider some simplifying assumptions to simplify the actual system to be a very simple model, for example, then this model can be used to understand the system dynamics and its relationships, right? Yeah, usually we start from a very simple model as a toy model, let's say, for an actual system, and then by understanding that, we extend that toy model to be so close to the actual system. Okay, so yeah, we can consider some simplifying assumptions, and then we can provide a model that is analytically tractable, so we can use the mathematical models of queuing theory. So here we can say that the mathematical models can provide us a rough cut estimation on the system's performance. Okay, and if we need to have more accurate and more detailed results, so then we have to do simulation, right, for the two complex systems. So here we can use that rough cut estimation provided by the mathematical models of queuing theory to verify the simulation model. Okay, so here you see that although we know simulation, we can use simulation, but learning and knowing the queuing theory could be useful. We can use them for verifying our simulation model, as you are going to do in your project in this course. Okay. The key elements in any queuing system or any queuing model is customers and servers. So customer is any type of entity that arrived to our system to request a service. For example, it could be a people, machines, trucks, patients, pallets, airplanes, email, cases, orders, and so on. So as you see here, it could be anything that needs service or process. And sometimes the server moves to the customer. We said that in our definition that customers arrive to our system, but sometimes server goes to customers. For example, a repair person moving to a broken machine. Okay, and server, any resource that provides the required service. For example, receptionist, repair personnel, mechanics, and so on. Okay, yeah, I mean any queuing system will have customers and servers. Okay. So here's the full list of the queuing system elements. So we have a calling population at first, including all the potential customers. These customers arrive to our system, then they will be in a queue, right? So, and then they will have the service, and then they will leave the system, right? So here we have a system, so the system's capacity will be one element here, right? And then the arrival process, how, I mean, the potential customers arrive to our system, in what rate, for example. And then we have queue here, so we'll have the queue behavior and queue discipline, right? And also we have service, so we'll have service time and service mechanism. So these are actually the key elements of any queuing model. Okay. The calling population includes all potential customers, and it could be finite or infinite. And in infinite calling population, we mean that the arrival rate is not affected by the number of customers who are already served by the system. So yeah, I mean, the calling population of customers is large enough, and after receiving the service by any customer, they will actually join the calling population again for a future service. So in this case, we assume that the calling population is infinite. For example, the potential customers of a restaurant or bank. But in finite population, finite calling population, we have a limited number of customers, and if we have some of them in the service or in the waiting line, they will affect the arrival rate of the remaining customers in the calling population. For example, a limited number of personal computers in a small company that may need to be repaired. Okay, and so yeah, as I said, usually for systems that have large enough population for customers, we assume that as infinite calling population. Okay. The system's capacity, the system may have a limited capacity for waiting lines. So the capacity of the system could be limited or unlimited. So in limited waiting line, for example, in a car wash, in an automatic car wash, we may have only room for only 10 cars to wait in line to get the service, right? So here, because of the limited capacity, we will have two terms for arrival rate and effective arrival rate. Okay, so effective is when we have an arrival but there is no room to wait, then that arrival will leave the system without receiving the service, right? So the effective arrival rate could be less than or equal to the arrival rate because of the limited capacity. And the unlimited waiting line, so the effective arrival rate is exactly equal to the arrival rate. So there is no constraint, there is no restriction on arrival. So here, for example, the in-person concert ticket sales for students, for example. So there is no limited room for being in line, for example. Okay. The arrival process of any queuing model is characterized by the inter-arrival time. Okay, so it could be in random fashion, or it could be based on scheduled times. So yeah, customers arrive one in time or in batches. So, and the size of the batch could be constant or again random. So the most important models for arrivals are these ones: Poisson process. In Poisson process, we assume that we have random arrivals. So I mean, the inter-arrival time between the arrivals is not constant, it's random, and it's occurring from a very large calling population, and all customers make independent decisions. This means that there is no dependency. I mean, there is no influence between the customers for making decisions about arriving the system and calling the service. Okay, and usually when we have, not usually, actually, when we have a Poisson process, this means that the inter-arrival time follows an exponential distribution. So all the examples that we had so far in chapters 2 and 3, where we assumed exponential distribution for inter-arrival time, this means over there we had Poisson process for arrivals. Okay, and we may have a scheduled arrivals like patients to a physician's office, or a scheduled airline flight arrival. So here we usually model the positive or negative deviations instead of having interval times. Okay, and the third one could be this: at least one customer is assumed to always be present in the queue. So the queue will never be empty, or server will never be idle. And for example, raw material in a product line. Okay. And for the queue, we have queue behavior and queue discipline. So queue behavior refers to the actions of customers waiting in line. So we may have these behaviors among the customers waiting in line: bulking behavior, reneging, and jockey. In bulking, this means that at the arrival, if the customer faces with a longer line than customer expected, then that customer will leave the system without joining the queue. So this is called bulking behavior. And the reneging, this means that the customer joins the queue, but after a while, when the customer finds out that the line is going too slowly, then that customer will leave the system again without receiving the service. This is called reneging. And the jockey behavior, this means that the customer moves from one line to another one if the customer feels that the other line is going faster than this line, for example. Okay, so these are the behaviors among customers waiting in line. And the queue discipline are the logics actually that orders customers in line. So it could be first in, first out, or FIFO or FCFS, last in, last out, LIFO or LCFS. LCFS, last come, first serve, or FCFS, first come, first serve. Okay, or first in, first out. Yeah, and last in, first out. So, or it could be service in random order, shortest processing time first, for example, and service according to priority. It could be presented by PR. Okay, so these are usually the disciplines that we may have for a queuing system. Okay. For service time and service mechanism, the service time could be constant or random. So in random service time, we assume that they are independently identical distributed. So ID means independent and identical distributed. So, and the distribution could be exponential, for example, variable, gamma, or log normal. Okay, and customers of different types may have completely different service time or service distribution, and in some systems, maybe the service time depends to the time of the day or the length of the waiting line. Yeah, maybe if the servers observe that the waiting line is too long, then they may work faster, for example. Okay, and we may have single server, multiple servers, or unlimited servers working in parallel. For example, if you have a self-service facility, it's usually characterized in the queuing system as an unlimited service model. Okay. So here we have an example here. Let's say we have the arrivals, and here we have two queues, Q1 and Q2. So in Q1 goes to a self-service center. So here we assume that we have unlimited servers. Okay, and in Q2 goes to a center with three, let's say, servers. So here we have three servers, and then at the end we'll have another queue, the third queue, which goes to a cashier with one server, and then after that customers will depart the system. Okay, this is another example including three machines. So we have a Q1 for machine 1 for candy maker and wrapper, Q2 for machine 2 as packer, and Q3 for machine 3 as sealer and wrapper. And as you see here, Q2 and Q3 for machines 2 and 3 have limited capacity. So inventory buffers have capacity of 1,000 boxes. Okay, so this was part 1 of section 1 of chapter 6. In part 2, we'll see more concepts and details about queuing models. Okay, thank you.